Chapter 2, P recovery. In Step 2, you will choose between P recovery before dewatering, P recovery post-dewatering, or no P recovery. If no P recovery is implemented, ammonia stripping cannot be selected for N recovery. Pre-dewatering P recovery processes involve harvesting struvite directly from sludge. The sludge is dosed with magnesium chloride and aerated to promote formation of struvite, which is then cleaned by washing with water. The final struvite product is high quality and comparable with struvite generated from well-established post-dewatering P recovery processes such as Ostara. Flow rate and HRT-based cost curves for post-dewatering struvite recovery were provided by Gerhard Forstner and his team at CMP. Pumping costs have been estimated using the influent and effluent TDH in global parameters. Aeration and magnesium chloride demand are estimated using typical airflow-liquid flow ratios and magnesium chloride per pound of phosphate ratios provided by CMP. Since these processes are proprietary, the user will not be able to customize these values. Outputs from pre-dewatering P recovery include required reaction volume, airflow rate, magnesium chloride demand, and mass of struvite recovered. Total annual costs account for pumping costs of sludge and air, as well as potential revenue from fertilizer sales. Capital cost is estimated using cost curves provided by CMP, and a 20-year NPV analysis is also shown. Thickening is a dewatering process by which biosolids are condensed to produce a concentrated solids product and a relatively solids-free supernatant. Gravity thickening uses the natural tendency of higher density solids to settle out of liquid to concentrate the solids. Polymer is added to aid in the settling. Gravity thickening is required for certain phosphorus recovery technologies and nitrogen recovery technologies, including ammonia stripping and ion exchange. Design parameters for the gravity thickener include the hydraulic resistance time, HRT, and percent solids capture rate. Average HRT is 8 hours. This value may be customized by the user. Average solids capture rate is 95% by polymer addition. This value may be customized by the user. For estimation of polymer costs, the percent activity of polymer can be edited by selecting Assumptions Global. The model-generated outputs include size of the gravity thickener, daily polymer requirement, total annual costs including polymer and electricity, capital cost for the gravity thickener, and 20-year net present value. The concentration of magnesium, phosphorus, ammonia, and pH are controlled to induce precipitation and growth of struvite crystals. Struvite crystallization converts soluble nitrogen and phosphorus into a particulate, inorganic fertilizer product. This is applicable to phosphorus recovery where effluent is low in solids, less than 2,000 milligrams per liter, and high in phosphorus, more than 20 milligrams per liter. The process is most appropriate for post-dewatered supernatant because high solids interfere with formation of the crystal product. Design parameters include specifying whether enhanced WAS release will be implemented, target phosphorus recovery, and stock concentration of magnesium chloride 2 and sodium hydroxide 4 pH adjustment. Typical phosphorus recovery is 85%. This value may be specified by the user. The stock magnesium chloride and sodium hydroxide concentration may be specified by the user. The model-generated outputs include phosphorus and nitrogen removed, recovered struvite product, effluent orthophosphate and ammonia concentration, mass of magnesium chloride required for struvite precipitation, volume of sodium hydroxide required, total annual costs including chemical addition, electricity, labor, and maintenance, potential revenue generated from struvite fertilizer, capital cost, and 20-year NPV.